Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great honor to introduce Professor Balazinska from University of Washington, Seattle. Most of you know her. She did her PhD at MIT. She works in the area of distributed systems and databases. Has a number of awards. It's hard to name all, but she won the Microsoft New Faculty Award, Career Award, and the 10-year most influential paper. In addition, she has a number of best paper awards. She works in the area also of scientific databases, which I forgot to mention. Mm-hmm. So today she's going to talk about the big data analytics. So without further ado.
Thank you, Surajit, and thank you everyone for coming. So before I start, I'd just like to acknowledge that the core technical pieces that I'll be talking about are actually the hard work of two of my students, Prasang and Youngchul. And also that this work is sponsored, actually, interestingly, by both the NSF and actually Microsoft. So thank you. So what is the motivation? The motivation, of course, is that everyone nowadays has a lot of data. Being on a university campus, we talk a lot more to domain or natural scientists more than industry. And all these natural scientists are generating data at just an amazing scale and rate. For example, astronomers are building these increasingly large telescopes that are simply, surveying the sky and accumulating very large collections of images, and they want to analyze these images. And here for the upcoming LSST, which is kind of the new survey, we're talking about petabytes of data. Similarly, in other domains, such as oceanography, they're both collecting data from sensors and also simulating the environment, simulating the oceans, producing large amounts of data. And in other areas, such as biology, we have new sequencing, new lab automation techniques. So the bottom line is that scientists are just producing a lot more data, and therefore they need tools. They need help to analyze all this data. And of course, as you perfectly know better than I do, that this need does extend beyond science. So if someone has a large amount of data, what can they do with this data? So there are several solutions that already exist. I could use a parallel relational database management system, perhaps GreenPlum. I could use a Mapreduce type system, such as Hadoop or Scope or one of those systems. Maybe I can use one of those new prototype parallel data processing systems, such as CyDB. And there are many, many challenges, many interesting challenges. And the one challenge I would like to talk about today is really fault tolerance. So what it is about fault tolerance? So if I'm going to analyze a large amount of data, clearly failures are going to occur while I'm processing that data. In a recent publication, Google reports that they see approximately 5 worker deaths, which means kind of task deaths for each Mapreduce job. So definitely failures are occurring. And the question then is, what should we do about these failures? And in the community, we really have kind of 2 standard techniques that are pretty extreme in terms of comparison. So one approach, which is characteristic of traditional parallel database management system, is to use kind of a pipelined, or if you want, streaming execution. So here, let's say we're going to start with a query that is going to start with a data set, maybe select some values, join with another data set, join with yet a third data set, perform some aggregation at the end. If I run this in a parallel database, I will typically start reading the data from disk, and then I'm going to stream the data directly from one operator to the next as I do my processing. I'm not going to write any data to disk. I'll just kind of stream the data right through all these operators, which can be spread across kind of several machines in a cluster. So this is great, but if something crashes during the execution of my query, well, I don't really have a choice. I have to restart the whole query. So there are several advantages. One advantage is that I don't actually pay any overhead of materializing, checkpointing, etc. I just stream the data right through. The second advantage is if my operators are not blocking, I do what is called, for example, online aggregation, online query processing, well, I have the possibility to produce results incrementally, which can be very nice if I'm going to analyze a large data set, to see the results incrementally and to be able to maybe stop the computation if I have seen enough and I'm not happy or happy. On the other hand, on the negative side, clearly failures are going to be costly, which at small scale is not a problem, but if I'm going to scale this up, then this might become a problem. So this is one strategy commonly used today. On the opposite side, we have Mapreduce types of systems, where the idea is to use blocking, to be extremely cautious, if you want, and to use blocking query execution. What we're going to do is start from the data is, again, in our cluster on disk, and we're going to read the data, process it, and write the intermediate results back to disk. Then we're done with the first operator. We're going to schedule the next operator that will read data from disk, process it, write it to disk, and so on. The beauty of this technique is that if something crashes, we don't have to redo all the work. We can only read the data from disk again and just reprocess the operator that failed. So the advantage of this technique is that recovering from failures is much less expensive than in the previous case because we only reprocess the one failed operator. On the other hand, there are kind of two negatives. One is that we do have to pay the overhead of writing all this data to disk. But the second negative aspect is that I can't see any results incrementally. Because I'm fully processing each operator and blocking, I really have to wait for the whole query to be done before I can see any results. So the question that we asked ourselves is, what would be kind of a nice compromise between these two techniques? What we would like is preserve the ability to produce results incrementally. We don't want to add any extra blocking just for the purpose of fault tolerance. And second, what we would like is to have a fast execution time, assuming that failures are going to occur. So how can we do this? So actually, can we achieve this? And actually, the answer is that yes, we can achieve this because there exist several fault tolerance techniques and we can use them in a non-blocking fashion. In fact, there are many ways in which we can achieve this. So there are many techniques. I'm kind of listing 3 here, and I'm going to describe them in details later. But the key question that we asked is, okay, great. So I can take a parallel data processing system. I can make it fault tolerant using one of several techniques. So which one should I use? And does it actually matter? So as a first set of experiments to kind of drive this research, we actually started with a small-scale cluster, kind of 17 machines, and we're going to run some simple queries and actually try to observe what happens when failures occur, and we use these different techniques for fault tolerance. So in these experiments, we're going to run simple queries. We're going to inject exactly one failure about halfway through the execution, and we're going to fail each of the operators separately in different executions, and we will average out the total runtime. And we're going to try to use different fault-tolerant strategies. So the first fault-tolerant strategy would be simply to do almost nothing. And if I have a stateful operator and the operator crashes, we're going to restart the operator from the beginning. But if I have some stateless operators, what I can do, let's say I have a selection operator in my query plan, that operator crashes. Well, if I restart the operator, I don't have to reprocess everything. I can simply skip over all the data that I already processed, and I'm going to continue processing. So that's very similar to doing nothing, restarting the whole query plan, except we're going to restart only one operator at a time, the operator that crashed. So in our small-scale cluster, we're going to compare. So here we're going to have the different fault-tolerant strategies. And on the y-axis, we have the runtime. The blue is the runtime without any failures. And then the red part is kind of the extra time we spent due to failure and recovery. So if I just run the query without any failure, this is the runtime that we get. If I run the query and I inject a failure roughly in the middle of the execution, so you can kind of see the expected wasted time because of the failure is going to be the red part. So in the case of something like a parallel database, if I just restart, then I'm going to add 50% because in expectation I have to redo half of the work. So what if instead I use this kind of technique of skipping over the input data whenever this is possible? So here indeed what will happen is the runtime without failures, kind of, the basic runtime remains the same, but in terms of recovery, I can speed up the recovery of some of my operators. I'm already going to do a little bit better. Yes?
For which operators are you using the skip?
So it's all the operators, but the stateful operators can't skip over anything. So they have to go back and actually reprocess everything because they have to rebuild their state. And you can see this, that I have kind of a little bit of improvement only for that operator. But that's still one strategy that we can use, yes.
So does the skip also handle indexes? Do you handle indexes?
In this case, this is, we were not really using indexes in this case. The main thing here is kind of, so I'll get to the details later of how we actually implement it in our context, because what you want is if an operator crashes, it needs the ability to tell whatever is upstream of that operator to just resend a certain amount of the data, not to resend the whole data, in order to be able to skip over some of the input.
So where is the state stored? This operator state that says...
There's no state. Also, in this case, to how much to skip over. So I'll get into those details a little bit later, because I'll basically show you how we implement it in our framework. So at this point, let's just keep it kind of a little bit vague, just to get a sense of, does it even matter that we check the right strategies? So this is just kind of one simple strategy. What if we also use the Mapreduce type of strategy? What I'm going to do is I'm going to write data to disk at the output of each operator, the way Mapreduce does it. But I don't actually have to do it in a blocking way. What I can do, instead of writing all of the data to disk and then sending it downstream, I can write a little bit of data to disk and then send that data downstream. Write a little bit more data to disk, send the data downstream. If an operator crashes, the advantage is all the data that the operator consumed is available somewhere on disk. So we can simply replay that data if the operator wants to recover, instead of kind of propagating back the failure and having to regenerate any of the missing data. So does this, how well does this perform? So here we're going to go back. We have again our query, and actually I forgot to say this is a simple query that selects some data, joins with another data set, joins with another data set, aggregates, and this is actually synthetic. This is not a real query, just a synthetic query. And it's about, I think this query was about 160 million tuples that we were processing. So we had our restart strategy. So in restart, what we're doing is simply if any operator crashes, we are restarting the whole query. In the skip strategy, if, let's say, my select crashes, well, I can restart the select and skip over the input data. We're not using indexes. We're just going to skip over wherever the operator started. If the join crashes, well, then the join will ask the select to reprocess. The select will kind of have to crash itself to reprocess, but it can skip over again all the data that we want, although the join will have to rebuild all of the state from the beginning. Same thing for aggregate. So skip, I guess, if select crashes, we can skip over some input data. If any of the other operators crashes, we pretty much restart from the beginning. In the case of materialize, we're going to write the output of select to disk, write the output of join. If now, let's say, this join crashes, well, we don't have to reprocess this join, but the join will just resend the data from disk, and that join will be able to rebuild its state from the beginning and continue, so kind of Mapreduce style. How helpful it is? Well, we actually executed this. In this case, for this query, it's pretty bad, because the fact that we have to write the intermediate data to disk really increases our runtime in the absence of failures. Of course, once a failure occurs, we can recover much faster, because we only have to reprocess the operators that failed. But overall, for this specific query, this is not the best strategy. There's one last very well-known strategies, and all these are kind of common strategies. We did not invent any of these fault tolerance techniques. The last well-known strategy from the community is checkpointing. So this is great for stateful operators, where we run the operator, and every so often we're going to write a copy of the operator state to disk. And if the operator crashes, we can restart from that last checkpoint, which will include the state of the operator and exactly how far along the operator was. Yes?
I'm surprised that disk writes are so bad in the previous slide. On a disk read, you have to seek to that block and wait for rotational latency. On a disk write, you can, in principle, find any blank spot on the disk right there and make a note where you wrote it. So you should have to, of course, the disk controller may not let you have that option.
Sure, and it could also be that, we didn't optimize all these techniques, as you could optimally maybe produce them, right? So this is also something.
So basically on an empty disk, just start writing where you are, right?
Sure.
Next time around, it's harder.
That's right. In this case, we don't do these types of optimizations. Right? I mean, we just kind of have an open file. The one thing we did have in this experiment is that each operator partition has its own disk. So we definitely do sequential reads, sequential writes. But that's as much as we do. All right, so and if an operator fails, we restart the operator from scratch, read the state from disk, and then process. So how well does this do? So we're going back to our query with the 3 techniques so far. And in this case, actually, if we checkpoint, we actually don't add that much overhead because the state is actually not that large. And now recovering is extremely fast because we only have to reprocess from the latest checkpoint. What is interesting, and this is kind of the bottom line and our motivation, is that given a simple parallel query and even a single failure, we can get something as much as 70% difference in execution time if we choose kind of the wrong, if you want, fault-tolerant strategy and the right fault-tolerant strategy. So the second question might be, so is it just that checkpointing is always the strategy that we should use? Is it always the case that I should simply checkpoint all the operators? Yes?
So when you do the skip, for the skip to be efficient, you need to kind of be efficient about it, right? So you use an index for that? How are you getting this improvement? Or you rescan and just not do the service?
No, you want to be able to seek to the right location. You don't want to scan the whole input data.
So you just remember
That's
the
right.
location.
Kind of at least the offset. Exactly. So here we're kind of scanning from disk at the beginning and we remember the offset and we just restart from that. Yes?
So this is for the Mapreduce setting too, right?
You could. So this is actually the experiments. So it was on the slide, but I forgot to mention it. We're using kind of our own, we're using a skeleton processing engine that all it has is operators and fault-tolerant strategies.
Because if you take Mapreduce, I would assume something like user-defined functions. A system like scope, user-defined functions are very important.
Yes.
That strategy like checkpoint might need an additional contract with the programmer to say what is even a right notion of a partial state.
Exactly,
So
and actually I will get to
operators
this. That's right, so what we did is we initially, let's just assume relational operators, we know their insides, and at the end I'll show you that if we have user-defined operations, then we can make assumptions that they can't do much in terms of fault tolerance, and you can still use our technique and you can still get improvement. So I'll get back to the user-defined operations at the end. So this is a very good question, yes?
When you say checkpoint, are you saying every operator is checkpointing?
Yes.
Because it may be possible that certain operators would prefer to do a checkpoint, whereas another operator which has much more state, the checkpointing would be much more expensive.
And that's exactly where we are headed. So the question that we asked, and actually this is a purely academic question. What I'm going to present is not something you could directly apply, but what we were just curious about from just a science perspective was, all right, so do I always checkpoint? Is there one strategy that's always the best? And the answer is no. And actually this is kind of the next experiment. What we did is simply replace the last, exactly the same query, processes also, the same number of input tuples, but we have a join at the end, and here the bars are completely different. In this case, the strategy of everyone just using, skipping over the input data when they can, no checkpointing, no materialization gives me the best runtime. So the observation here is that if I have a parallel query, the choice of fault tolerance technique can have a significant, a visible impact on runtime, even in the presence of a single failure. So imagine with more failures, the differences will amplify. At the same time, there isn't like a single well-known technique that I can just apply uniformly. So what we want is exactly what you suggested. We said, should I pick the right fault tolerance technique at the granularity of each operator? And we actually went further. And the question we asked was, can we build an optimizer that will take my query plan and my resources as input and will automatically tell me what fault tolerance strategy to use at each point in my query plan? And does it actually matter? Would such a fault tolerance optimizer make a difference? So that's the question we're kind of set off to answer. And in the rest of the talk, we'll kind of see how we went about answering this question. Does that make sense so far? Yes?
What is the cost function for the optimization? Is it just runtime, or is there latency, any other factors?
So I'll get to this in a second, kind of exactly, because that's something we can't just use the standard cost functions. And one of the challenges is here, we really try to get as close as possible to estimating something equivalent to runtime. And because fault tolerance, the difference between different fault tolerance plans is not orders of magnitude. It's in the order of, with one failure, maybe 50%, 40%, 70%, and I have to be a lot more accurate in order to select kind of a good plan. And one challenge is that these operators interact with each other when they're running in a pipeline. So if an operator is like a symmetric hash join, initially it's going to be, the bottleneck will be how fast the input data is arriving. But soon it's going to produce so much tuples, the bottleneck becomes the CPU at the operator. So we had kind of challenges in dealing with these techniques. And I'll come back to this in a few slides. So the bottom line so far is that we want to see if we can choose fault tolerance at the granularity of operators and if we can make this choice automatically. So this is what we did in our optimizer that we called FTOpt. And the reason why it's so short is because the paper was kind of over the limit, so they need kind of a short name to squeeze the paper. And this is actually in a last year's SIGMOD conference. So the goal here was kind of really two things. First of all, I need the ability to mix and match fault-tolerant strategies. So I'm going to have a single query plan with one operator using one strategy, another operator using a different strategy. So the first thing we had to develop is some sort of protocol that will hide all the details of the fault-tolerance technique and have some sort of high-level agreement between operators such that if one operator crashes, we only restart that one operator and we don't care what anyone else is doing for fault tolerance. So that was the first contribution. And the second one was really to have this cost-based optimizer that we call a fault tolerance optimizer. The input to the optimizer is the query plan. So we first run the regular optimizer, get a query plan, and then we pick the right fault tolerance strategy for the query. And of course, the question then is also kind of how much do we gain? So kind of once we actually start to execute it in parallel, the way this is going to work is we're going to kind of encapsulate these operators. We're going to have our optimizer on the side, and we'll have this encapsulation with the protocol between operators, and the optimizer will select the strategies, and then different operators will end up using different strategies. So the granularity will be really kind of one operator in the query plan. So let's first look at the actual protocol that we use. So the goal is that we're going to have pipelining. We don't want to add any kind of blocking. I want the data to flow continuously because if at all possible, we would like to be able to show results incrementally. We don't want to, for fault tolerance, to add any kind of blocking. So that's the first goal. That will be kind of the goal of the protocol. And at the same time, we need this ability, kind of people raised questions about figuring out where do I restart from, what do I reprocess. So the protocol has to capture this. So here's kind of, this is best illustrated with an example. Let's have three operators, O1, O2, and O3. Our protocol really requires that each operator obeys 4 different rules. The first rule that we require is that all tuples that we send, or all records, if you want, between operators must have some sort of unique identifier, like a primary key, or it could be a hidden record ID. And the reason is because we will, when we restart an operator, we will want to tell the upstream operator where to resend data from. So we need the ability to identify these tuples uniquely. So we need those unique identifiers. Second, we will request that if an operator at any point in time, O2, is allowed to go back and ask O1 to resend any kind of suffix of its output data. So I can say, go back and say, please restart and send me everything from the beginning. Please restart and send me everything since tuple number 225. And this operator has to support this feature. The easiest way to implement this is if this operator says resend everything from tuple 225, this operator can simply kill itself, restart, reprocess, and kind of send all the data, just delete all the output data until it sees the right tuple and then continue. And of course, this does assume that we have determinism in the operator. So we do not support operators that have some sort of randomization inside of them, because we will assume that we can restart an operator and it will produce the same output. Yes?
I take it pseudo randomization is okay?
That's right. So if you have some sort of random seed, then I can just give you the seed again. As long as there's some way to restart and regenerate the same sequence, we're fine. And we discussed this in the paper. I'm not going to go into the details of that aspect. All right. In many cases, if I require that an operator remembers all its output and has the ability to reproduce its output, that's fine, but it can be actually quite costly. And in many cases, operators, once they know they have made a certain amount of progress, let's say maybe this operator chose to checkpoint, then this operator knows that it will actually never ask for some old tuples again. Well, as an optimization, this operator can actually acknowledge to the upstream operator and say, by the way, I will never ask you to replay anything before tuple number 153 because, it's my problem how, but I know that I will never ask you for this. And then if this operator uses something like, maybe materializing the output to disk, then it can truncate its logs, it can do whatever optimizations it wants. And finally, the last rule, we're going to ask all the operators to remember the last tuple that they received. So if this operator crashes, it can actually ask O3 and says, okay, I just crashed, tell me what is the last item that I sent you and that you received. And then this operator will then ensure that it eliminates duplicates and only sends the new data. Yes?
You always require the sender to keep the output. Why don't you have the option of this operator itself to put the input into disk somewhere?
It can do whatever it wants. So here all I'm doing is I have 4 rules, but I don't tell the operators how to implement them. I just say that the operator needs the ability, and the easiest way would be this operator could do nothing except if someone requests to replay it, could just crash itself, restart, and regenerate it. So we don't put constraints on what the operator, how the operator implements those rules. Does that make sense? Or was the question different?
Like O2, right? If it's crashed, if you store the input in locally, you can get the data from locally rather than go to the O1 to.
Oh, yes. And you'll see this on the next slide. Exactly. So what kind of the main observation here is that we have these 4 rules, but they don't say anything about checkpointing, materializing the output. They don't say anything about how to implement it, which means as long as the operators can play by these rules, they can do whatever they want. And here's one example actually with, let's say, checkpointing. So let's say you go through this example, and operator O2, the middle one, crashes and restarts. What the operator will do is first it can actually ask the downstream operator O3 to say, what is the last tuple that I sent you? And that O3 should be able to reply by kind of the rules that we have about identifying tuples uniquely and remembering the last tuple they received. So now O2 knows kind of when it crashed with respect to the downstream operator. At that point, O2 can do the following. If it happened to save data from on disk, it can recover that checkpoint from disk. If it didn't have a checkpoint, well, it restarts from the beginning. But it's going to basically either recover state or start from scratch. And depending on which of these alternatives the operator used, it's going to ask O1 to replay a certain amount of data. If O2 checkpointed, well, maybe it will ask only for the most recent few tuples. And then maybe it will be efficient because maybe these few tuples are still in memory at the preceding operator. But if it didn't, and it has to restart from the beginning, well, maybe it will ask to replay all the data from the beginning. And finally, once O2 gets the replay data from O1, it processes the data and waits until it catches up to the last tuple, and then sends only the new data to the operator. So what is nice is that we have several nice properties. First, the data can flow continuously in the absence of failures. We don't put any constraints on when data has to be written to disk. There's no blocking. The data can just flow continuously. At the same time, if an operator crashes, we can restart only that operator individually. And finally, we don't put any constraints. As long as I have come up with my own fault-tolerant strategy, if it can be made to work within this framework, then I can use that strategy for any operator. So the kind of many benefits. And what actually we did is that we show in the paper how to implement the standard strategies like checkpointing, materialization, and skipping over data within this framework. Yes?
So I have a question about the comment you made about blocking of operators. So if O2 fails, and until O2 recovers, O1 has to buffer its output somewhere, right?
Yes. So actually what happens in our framework is when a failure occurs, then we do block. Then we actually block the whole query plan.
In a failure, there is a blocking.
Yes.
But without a failure, I think your comment was without a failure, then there is no blocking.
Exactly. But when a failure occurs, we indeed block the whole query plan.
Okay.
Which is why we often have these graphs where we have the runtime without failures and then the recovery time we just add it up. Okay. Because no one is doing anything during that time. Yes?
How does an operator remember the last tuple it's consumed in the event of an upcoming crash?
So one example would be the operator could simply hold it in memory. So if let's say O2 crashes but O3 didn't crash, then O3 could just have that information in memory. If O3 crashes...
What about O2 which crashed? When you try to resurrect O2,
yes,
it may have done an awful lot of work that it doesn't want to repeat.
So if it checkpointed the work, so it depends what O2 did. If O2 starts, checkpoints nothing, crashes, it pretty much has to restart from the beginning, unless it's a stateless operator. If O2 is a selection, then it can just ask O3.
Go back to the previous slide, please.
This one.
So, I see. So, if I act a tuple, at that point, I need to do something that will persist what I
Yes, exactly, exactly. And here it depends on your failure model. If you assume that only, like in this paper, just for the purposes of exploring the idea of fault tolerance optimization, we restricted ourselves to process failures. We just did not assume that disks will fail, just as a way to explore this idea without too much complexity. But if you assume that disks can fail, then perhaps O2, before it can acknowledge, not only has to write it locally, but maybe has to replicate it somewhere else, and then it can acknowledge it. But that would add overhead to your fault tolerance strategy, and then maybe twist this kind of, push the scale towards not using any fault tolerance, because you might as well restart. Otherwise, it's going to be too much overhead at runtime.
A system like Hadoop or Cosmos for that matter, it's these kinds of considerations that skewed them towards a very, very low fault tolerance kind of model. The overheads of introducing even moderate granularity recovery become hard, they become complicated.
They become complicated, that's true. And here that was kind of a first step towards saying, is this even worth it? Because if it doesn't work at that level, then there's no point going forward. That's what I'm saying. I'm saying it's not exactly practical directly. It's kind of just an interesting scientific question on that path. All right, other questions? So this is for the, yes.
So in the context of databases for suspending and resuming queries, people have looked at the whole idea of operators establishing contracts with upstream operators so that they can either choose to check one year state and start at that point, or invoke the contract and essentially allow the upstream operator to replace certain parts of the state to be able to rebuild an operator. So how does this fit in comparison to these kind of contracts?
So the main difference compared to a lot of the work, including this type of work, is that this is really meant towards enabling the heterogeneity. So there's a lot of protocols that are kind of similar in spirit, but they assume sort of homogeneity. Everyone is checkpointing. Everyone is skipping over. Versus here, we really thought, what is the minimal set of primitives that we need in order to decouple the choices of the strategies? But a lot of the principles, such as acknowledging a tuple, replaying tuples, they will kind of come up in different protocols, but typically everyone is doing some sort of uniform strategy. Or you might have, or the contract will be specific to a specific pair of strategies. Versus here, the contract is independent of the pair of strategies, and that was kind of the main goal. Other questions? All right, so we've seen kind of we've seen the protocol. So the second part, which goes back to the other question, was with respect to actually the cost model. So here we want to make the decision on the fault-tolerant strategy to use in an automated fashion. Therefore, we need some way to compare the cost of these different strategies. So the cost function that we chose to optimize for, and you could pick other cost functions, was the execution time with failures. So the cost formula is going to be, we're going to try to minimize the time that we spend in regular processing, which is blue, which means the time for the first tuple to propagate through our whole pipeline. Remember that we assume we think about non-blocking. Although if an operator blocks, it's simply that it delays the first tuple until it's done processing. So we have kind of time for the first tuple to propagate, and then the actual processing time then for the remaining tuples to go through. Plus, because as has been mentioned, we block during failure recovery, we're going to add the expected kind of number of failures times the time we're going to spend recovering from these failures. And this is kind of reasonably standard cost function to optimize for. The challenge, though, is when we started with standard cost formulas, we were getting highly inaccurate results. And like I mentioned, in a query optimizer, the differences between different query plans can often be orders of magnitude huge. So even if the cost functions are not perfectly accurate, that's fine, sufficiently good to just pick reasonably good plans. Here we are talking about 50%, 40% differences in runtimes between the different fault tolerance plans. So we needed to be more accurate in terms of the cost models for the operators. And the key thing that we actually observed when executing our pipelines is that there's kind of a lot of dynamic between the operators. In particular, an operator will not necessarily produce, like a selection operator will produce, it's a filter, right? So I get an input tuple, apply some filter, output the tuple. This is going to be a kind of a linear operator that's kind of producing data at a steady state. But many operators start empty and then they start to accumulate state. And they have this kind of nonlinear behavior that when we were not capturing, we had just kind of too much of a difference in terms of the predicted and the actual runtime. So kind of the way we chose to solve this is by using kind of a convex optimization framework and to just model the operators with constraints of the form. If I put two operators together, well, the input rate for this operator cannot be any higher than the output rate of the preceding operator. And the rate at which this operator is producing tuples cannot be any higher than, let's say, how much the CPU allows me to produce. So we're going to kind of model operators with all these kinds of bounds. And here's one example for the symmetric hash join operator. So the idea behind this operator, this is one example, is that we're going to read data. As the data appears, when we have an input tuple, we put it in an in-memory hash table. When I have a tuple from the other relation, I probe my hash table, and I also store this tuple in my in-memory hash table. Next tuple comes, I probe the other relation, and I store the tuples. So at the beginning, when the operator starts running, actually no, so if I assume that all the data is available to me, there's a certain maximum rate at which we can produce tuples, which is how much CPU we have available to us. Yes?
I have a basic question. So
yes.
Just to clarify, so you have an optimal plan, which optimizer already built.
Yes.
And for each operator in that, what are you trying to find out?
So this is a good question. I should be more clear.
How much to materialize, whether to materialize.
Exactly. So what we want to do is for each operator, we will decide which of our n available fault-tolerant strategies to use. So should this operator skip? In our experiments, we looked at skipping, checkpointing, or materializing. And if I pick checkpointing, then how frequently should I be checkpointing? So when you materialize, you only materialize the output. When you checkpoint your internal state. So the overall optimization is going to be that I have my cost function, and each operator has a variety of fault-tolerant strategies available to it. For each fault-tolerant strategies, we need a model that will help us assess what will be the cost of that fault-tolerant strategy.
Either it checkpoints all of its output or it doesn't checkpoint any of its output.
That's correct.
There's no option of like checkpointing part of the output.
No, we don't do that. We just either checkpoint or not, and if you checkpoint, the only decision will be the frequency.
So,
yes?
Earlier you gave an example saying difference between two strategies could be as much as 70 or 80%.
Yes.
So I would say that alone doesn't motivate a complete optimization framework. There could perhaps exist one strategy that comes within 20% of all things.
Yes.
So in which case you don't probably need the search space.
I agree.
Know, maybe such a strategy doesn't
I
exist.
agree, and actually this is a kind of, I totally agree. So in this case, we really wanted to explore the idea of the whole optimization. But I agree that in practice, you might want to take one of those simpler strategies because you might get within, 20-30% of optimal. I totally agree, yes.
This may be off subject, but anytime I quoted John Massey saying some people do unspeakable things for 10%, my boss Bob Davidson will say we do unspeakable things for 3%.
I see, yeah, so it depends on the
20%
perspective.
for product managers is a big number.
Big number, yeah. That's right, but I agree that this is kind of, that's why I say it's kind of more of a scientific interest that we wanted to see how well does it work.
In theory, if the spread is 70%, it's reasonable there may be one that's always in the middle. But whether there's one that's consistently in the middle is unclear. Right? It may be that any given strategy is either lousy for some inputs, in which case this is completely out of code.
That's right. So this is, at least we want to eliminate the bad plans. And we actually did a lot of sensitivity analysis to see how sensitive we were to different bad inputs. But the bottom line, just kind of going back to the cost functions, is simply that if I take an operator such as a symmetric hash join, if all the input data is available, then the output rate is kind of limited by how fast I can process this input. But typically, the input is coming at a certain pace, and as it goes, I'm accumulating more states, so I'm finding more joins. So actually, initially, the output will be limited by how fast the input is arriving. So when we combine these, what eventually happens to the operator is that initially it processes as fast as the input is arriving, but eventually it becomes CPU bound, and then it kind of cannot process any faster once it accumulated a certain amount of state. And what we found is that we actually, because this is something like 25%, and we were talking about differences in the order of 40%, we had to account for this type of effect in order for the optimizer to actually give us select good fault tolerance plans. Yes?
Why did you consider yourself to work with the optimal plan? You could have instead looked at all the plans of each.
Oh, I agree.
Overall the
Yes.
best plan, right?
Yes, and that's possible. We just didn't do it. But that would be possible to kind of expand the search space and look at kind of do it with the optimizer. That might be interesting. Yes?
So many operators have this natural points where it makes perfect sense to checkpoint. For example, the minimal heap state points. For example, in a block-based nested loops join, you know that when you have completed one outer page, and then basically your heap state is essentially negligible. So these are optimal points for doing a checkpoint strategy. So so I'm trying to understand how those specific choices would relate to this general kind of technique.
Framework. So that would be maybe one way too. When we actually look at the optimizer, here we said just what is the frequency, and saying that if I just pick the frequency without the specificity of the operators, then I'm going to kind of get an average size with a certain frequency. But it is in fact the case that for some operators there are certain points that make a lot of sense. We could restrict the optimizer to only look at these points and say for these operators the frequency is limited to being only one of the following, and then only get that those best points indeed. Exactly. So how well does this model work? So this is actually, this is actually kind of a good case where when we have different operators, what we did is we actually looked at different pairs of operators with different combinations of fault-tolerant strategies. So skipping, materializing, skipping, and this is the comparison of the real runtime with the one that we predicted. And as you can see, we're not always completely on spot. There are still differences, that may be in the order of 10%, but at least we can distinguish between all the main plans. So this is as far as we wanted to get. So how well does this? So kind of the final question is, so now that we have this optimizer, so we have the ability to use different fault-tolerant strategies, and we have the ability to pick these different strategies. So the question is, are we able to find these good plans, and how much faster these plans actually execute? So this is one example from our paper where we have a query kind of similar, select, join, aggregate kind of standard query. And this is a query that was actually processing 160 million input tuples, producing 8 million, I think the first join, the select outputs 8 million, then we add another 8 and another 40, and then the aggregate has a state of 8,000 tuples. So that's kind of the query plan. And as you can see, we see different strategies: restarting, skipping, materialization, checkpointing. And for this operator, this is one of the examples where really a hybrid strategy was helpful. And the hybrid strategy ended up being to materialize the output of the select, do nothing for the joins, and then checkpoint the state of the aggregate, which is a little bit kind of what we could anticipate. And the difference was significant. It doesn't look as impressive from the graph because we're not talking about orders of magnitude, but still the hybrid plan was 20% better than any of the uniform strategies, and it was definitely better than 33% better than just restarting. And if you look at the choice between kind of the best and the worst possible plans, in this case, it was also in the order of 33%, which is significant. That's like a third of your query runtime, which is nice. So let me just kind of quickly show a couple more results from the paper. This is kind of another example query that shows how many million tuples we are processing. None actually is the same as skipping. This is the same as skipping. And this is another example where we show what we predict, what we observe, and at least it shows that versus restarting, that in this case the best strategy was to uniformly do nothing, and our optimizer was able to select that strategy. Another example where we have, this is kind of also important. This is select, join. This is the same query, select, join, with slightly lower selectivities. And suddenly the best strategy is to actually materialize. So given same operators, but we just change the input data, now the best strategy changes. And again, our optimizer is able to find that strategy. Although in this case, because there was a little bit more of a kind of network, higher network consumption, then we actually had, actually not this one. Our estimates were not as accurate, but still accurate enough to find the right plan. We changed the query plan a little bit again. We changed and have an aggregate operator. And this is where, again, kind of the best strategy here was to checkpoint. And we were able to find it. But this is the one where we actually, oh, that's right. This is the one where we're producing quite a lot of tuples. Some operators were network bound, and our cost model was not as accurate for network bound operators, more accurate for CPU bound operators. So our estimates were not as accurate, but we still found the right plan. And finally, kind of again, small twist on the query, this is where we have a hybrid plan. Actually, this is kind of the same as I showed earlier. This is the hybrid plan where we materialize, skip, and an aggregate at the end. But this one just shows also what our estimates. Yes?
How do you model the number of failures? That seems to be a very important parameter.
This is very important. So how we model it is that typically, I mean, at least from what you read in papers, is that often people know that in their specific cluster, there's a certain number of kind of average number of failures per job or average kind of mean time to failure or some of those statistics. So what we do is we say, given that I have a query, I can kind of estimate roughly how long it will run for and how many nodes I want to use for it. And then I will estimate, so how many failures do I expect? So I expect this query to run with 5 failures, 6 failures. And then we optimize for the runtime with that number of failures.
Find that your strategies are very sensitive to that. So let's say you change that.
So actually, no. So we found that. So we did a sensitivity analysis. Do I have that later? So we found that we were actually, and we have the exact result in the paper. We were not sensitive to small wrong estimate in the number of failures, and also we were not sensitive to I/O performance estimate, like writing data from disk. The one point that we were sensitive to, of course, were cardinality estimation errors. Within 10%, we can do quite well, but when we were off by more than 10% or more, then we started to not choose the right plans because we were thinking like, hey, it's great to materialize, and then discover that there's actually so much data. So that was the sensitivity. And finally, to go back to the impact of user-defined operators. So this is one example plan. What we did is we replaced the final aggregate with a user-defined operator. So we assumed that the best plan, in this case, the hybrid one, had the last operator checkpoint, and that was the runtime we would get. But here we replaced the operator with a user-defined operator. What we do with those is we assume they're unable to do anything in terms of fault tolerance. So now we have a query plan. We can pick fault tolerance strategies for all operators, but some of them don't know anything about fault tolerance. And actually, we show that it's still useful, even if you have some of those operators. We pick different plans, and you can still do better than some of the uniform strategies, such as, for example, materializing on behalf of the operator. So this is to go back to the user-defined operator question. So how much time do we have? 2:30? Or we have time? Okay. So this is just kind of ongoing work. So like I said, this was interesting. So what we noticed is that it is possible to use different fault tolerance strategies in the same query plan. We can pick them automatically, and it does make a difference that's visible on the actual runtime. The key challenge, though, is we need these specific models for the operators. And that's really painful because it's hard to get accurate models. Like in one example where it was really network bound, our models were not that accurate. And it's hard if I want to write new operators to develop these models. So where we are headed right now is to say, let me forget about these models. What I'm going to do is I'm going to start and run a query in parallel, and I'm going to use maybe some sort of fault tolerance strategy, like materializing all the output. And as I run it, I'll simply observe what is going on. And if I find that I have some bottlenecks, I will try to remove maybe some fault tolerance or materialization points dynamically at runtime, and that will allow me to do better. So that's kind of what we're exploring right now. So kind of in terms of summary of the whole fault tolerance work is that we looked at the problem of running queries in parallel, whether it's worth to materialize, checkpoint, and do these different strategies. Some of our contributions was to say, look, if I have a parallel query, I can actually run the query and make it fault tolerant without blocking. I can pick and choose the technique, and I can do this automatically. So that was kind of the main point of the whole fault tolerance work. And where we're headed, like I said, is more towards the dynamic scenarios. So any questions at this point? Yes?
You said you are working on learning about the model, cardinalities, crash the system, redo the plan, and restart with the new better model cardinalities, do you have a chance to change the plan shape then, or?
Oh, that's a good point. We actually do not change the plan of the shape at that point. That's right, but we could. This would be something also interesting. Especially that what happens is if we crash and one node is restarting from a failure, no one else is doing any work. So we could take that opportunity to make some changes at that time, since the other nodes could be doing some other work while we are replaying. Right? So yeah, so if you're working in that space, that might be interesting. That's right, yes?
So after all the analysis, did you find any patterns, as in like some strategies are good for some operators irrespective of, like for example, materialization is good for aggregate operators? Or
so what we found is we actually found some patterns. In particular, if I have stateful operators, then it's often the case that the operators right before, if they frequently, the best strategy is to materialize before that operator. Or state operators that have small states, they can definitely checkpoint. But we often found that it's not for one specific operator, but it's for a combination of pairs of operators or sequences of operators and also the input data sizes. But in that case, yes, we did kind of find some patterns that if I have a sequence of operators with stateless operators and then big stateful operators, it's often worth to materialize the output of those stateless operators. But it's hard to just make that general. These are still kind of things we kind of see, but it's a cost-based model kind of allows you to formalize that intuition, which is the case. Other questions? Yes?
If you have a user-defined operator with a recovery strategy of none,
that's right.
And you put it on one of these Google jobs that have an average of 5 crashes. Will the job ever get done?
Well, it does, because we still restart that user-defined operator from the beginning, but we only restart that operator because the operators around it can provide fault tolerance and things like replay, which is, we definitely don't want to reprocess the whole query.
Any other questions?
And actually, if you have a few minutes, I want to just give, I don't know how many minutes we have, that's what I'm asking.
Okay.
Do you have time? Can we go over 2:30?
Yeah, sure.
All right. So what I want to do is to kind of, that's all I want to say about fault tolerance. That's why I'm pausing here. And I can't remember how much time we allocated. That's why I'm hesitating. But I wanted to just give you kind of a very broad overview of the kind of research that we're doing in our group besides fault tolerance. And really, and this is something I'd love to talk to people offline. So we really are doing work along 3 broad aspects. So we are on campus. There are a lot of scientists. We talk to them. All of them have a lot of data. And we find that there are really challenges along 3 lines of work. First, how can I get someone like a scientist who's technically skilled and capable, but wants to run complex machine learning and complex user-defined operations and other analysis? How do we get them to do this efficiently? And of course, we can leverage cloud computing environments, and this is our Nuage project. And what I talked about is an example project from within this umbrella. The second is to look at not only making things go fast, but also making them easier to use. And we're not HCI people, but we're still looking at things such as how can I help someone articulate a SQL query? Can I use past executions, past usage history from the cluster to learn what kind of queries people ask and help newcomers articulate their own queries? And finally, the last one that we're looking at, which is actually related to the Windows Azure data market, is to figure out how can I price. Now, a lot of people have lots of data. They all want to buy and sell this data online. What kind of database support do we provide to make it easier for them to articulate prices, reason about prices, price only a couple of views, and then automatically have them sell arbitrary queries, and so on. And just to kind of give you quickly some examples of projects in these different categories, in terms of, let me give you kind of a couple of projects in the efficiency categories. So we worked with a lot of scientists, and one thing we discovered time after time is that often when jobs execute, there's a huge skew. So this is one example where it's a debug run, so it's a smaller scale. On the x-axis, I have time. On the y-axis, I have all the tasks that I'm running in my cluster. And I have different colored tasks. They don't really matter here, but you can see the duration of all the tasks is very, very small, except for this one crazy task at the top, which takes forever. So what we build is we actually have a couple of systems that allows us to smooth this kind of skew automatically. So the top line is 1.5 hours versus more of the other, lines in this job is actually, or just in the order of a couple of minutes. So we build a system called Skew Reduce, and the details are in a SOC 2010 paper. That is also actually an optimizer. It takes as input a sample of the input data, cost functions about the actual processing that we want to do, information about the cluster, and figures out how to partition and allocate the data in a way that automatically kind of gets rid of this type of skew. And what is interesting is on real scientific workloads, we found runtime improvements of a factor of 6 to 8 compared to a standard Mapreduce implementation. So this is really significant. But that was specific to one type of applications, kind of that we find in the science domain. We also have a more recent SKU work where we said, I don't want these like here. I have these cost functions. So in the new work, we said, I don't want any information from the user. And what we do is we simply observe what is going on in a Hadoop cluster, notice when SKU is occurring, and then find a good way to kind of reallocate the data in a manner that introduces low overhead and kind of looks ahead to try to optimize for our total runtime. And without knowing anything about the application, we can reduce runtimes by a factor of 4. So this is significant. These are, large factors. And those are real systems that are actually built on top of Hadoop and publicly available now. And actually, my student who worked on this is going to join Microsoft in September in the Bing search team. So you'll guys get those skills now. We also looked at iterative processing. So a lot of people want to use Hadoop clusters, but they need to run machine learning, page run kind of algorithms that iterate. By simply being smart about caching and scheduling, we can cut runtimes in half. And this is also a system that is now publicly available that we built at UW. We're also collaborating with the SciDB team, which the goal here is to build a parallel system that is different because it's going to operate on multidimensional arrays. So scientists often they simulate, the universe, they simulate the atmosphere, they operate on these multidimensional arrays. And this is a new system, but already has some 500 downloads. And this is not our work, this is joint work with MIT, Brown University, Portland State University, and so on. So this is kind of examples from this category. In terms of making big data analytics easier, I mentioned that we do different things. So we looked at SQL autocomplete. And the idea is that as a user kind of types a SQL query, the user can ask for recommendations. And what we are going to do is to say, OK, so the user has put certain tables, certain predicates in their query. We look at that query, we look at past usage of the cluster, and see who asked similar types of queries and what other predicates, tables did they use in their queries, and then we recommend the most popular from those. And we actually had good, we tested this on the Sloan Digital Sky Survey query log, and we had kind of very good results in terms of the type of recommendations. We also built kind of another thing that allows people to browse through queries, but I'm not going to mention this. We looked at other things that try to help people understand their cluster better. So once they actually articulate their query, they run it in a cluster. We looked at things such as better progress estimates that allow people to have a better sense of how long their queries are going to run for. And one of our key contributions was to say, well, failures will occur, skew will occur. So instead of giving one best guess, we're going to actually give people ranges where we try to kind of make the range as small as possible such that it is useful and say, this is kind of the best case runtime estimate, but assuming kind of a single worst case failure or a skew at the following operator is quite likely, then we're going to also give users a range so they can have a better sense of how long their queries will take. Most recently, we actually built a system that actually I'm pretty proud of. So what we can do is we can run a Hadoop job, and then we can ask questions such as, why did my Hadoop job just run slower than this other job, even though it processed less data and it was running using the same number of instances? And our system uses machine learning to then say, well, because between these two runs, someone, for example, changed the cluster configuration and increased the block size, and therefore you're actually not using all those machines, perhaps. So this is something that will appear at the PVLDB. So this is kind of a few examples from this area. And again, I'm really happy to talk to you about this offline. And finally, the pricing. This is the most recent project. And this is actually quite fun. So we're looking at this from several perspectives. So the first idea is that people buy and sell their data online. Currently, if I use something like the Windows Azure Data Market, I can't price my data, but I can only price it using kind of very simple selection queries. So I'm going to define kind of a view, and people can enter parameters in this view, and then they're going to pay based on the number of output records that they get. And you kind of pay monthly based on kind of the total amount of data you will be seeing. What we actually asked was to say, well, if I produce a certain number of views, then my customers, when they come, they will have to pick among one of those views to satisfy their needs. But if none of the views is good, well, they will have to buy some superset. And if they're not willing to pay for the superset, well, they might not really be happy. So what we did is we actually built, so this is more on the theoretical side, we developed theory that allows us to allows the seller to only specify some views, and we use these price points to automatically derive the price of any arbitrary query that the seller wants to purchase. We basically automatically figure out, given the query that the user is interested in, what is the minimum number of views that they have to purchase and in what combination to get the best price. And we can do this automatically for a pretty large selection of queries. And this kind of pricing idea goes even much further than just pricing data. We're looking at things such as, if I'm going to buy and sell data, I also want to protect the data. I will sell the data and say, you're allowed to use this data, but you're not allowed to maybe join the data with some other data sets. So we are now looking at building databases that can help us enforce these digital rights on the data without too much overhead. Or if I'm going to use cloud computing resources, many people share the same cloud. I need a way to figure out what optimizations to implement, how to price these optimizations, how to allocate the cost, how to give it to the users. And we also have automated techniques to do this. So this is kind of, in conclusion, kind of a broad scope of the kind of work that we do in the database group at UW on the system side related to kind of big data analysis, cloud computing, and data pricing. So, okay, at this point, yeah, that's it. Thank you very much.
Any final questions? I think we had a fair number during the talk. So.
Good. All right. Thank you.
Thanks so much.